Okay, I think we're going to start. So I'm Samuel Conseil. I'm going to share this first session. So we're going to have two talks. The first one by Antimo Marrazzo on Wannier function and the ecosystem. This will be followed by another talk by Tristan on many theories. And so, yeah, Antimo, the floor is yours for about 50 minutes, and that will be some questions.
Okay. Can you hear me? Okay, so thanks a lot, Samuel, and in general, thanks a lot to Professor Feliciano Giustino and all the organizers for setting up this beautiful event and for inviting me here to talk to you about Wannier functions today. So my name is Antimo Marrazzo, and I work at the physics department of the University of Trieste in Italy. So I will follow up on what Paolo said yesterday. So if you don't know where Trieste is, it's 80 kilometers from Udine. So and before I start, I want also to acknowledge Giovanni Pizzi and Junfen Chao from a PFL, from the group of Nicola Marzari, who gave the talk yesterday, because they contributed a lot to prepare, especially the material we'll present for the hands-on tutorial later on today. Okay, so the title of my talk is The Wannier Functions Ecosystems, Fundamentals and Recent Developments. So by now, you should be somehow familiar with the basics of Wannier functions. This is, you have been introduced to the topic by Nicola Marzari. Higher. Better? Better? No? Okay, so you've been introduced to the theory of Wannier functions yesterday by Nicola Marzari. So today I will focus a little bit more on, on the practicalities on running the code, on the code Wannier 90 itself. We'll see what that is, but also give you some perspectives of this idea that we are moving from, I think, community was really built around the code of Wannier 90 to a broader community of people interested in doing things with Wannier functions. And indeed, okay. So the core of my presentation will be Wannier 90, which is the software. It's an open source software written in Fortran and modern Fortran to calculate Wannier functions and related quantities, especially operators represented in a Wannier functions basis. But I think the modern way to look at this code and in general to look at this problem is to think Wannier 90 as the center of a much broader software ecosystem. Okay, so this is a slide that I borrowed from Arash Mostofi, where we're trying to put together a number of codes, and by far this is not a complete list. There are many more codes than I'm presenting you in this slide. And these are some of the codes that are interfaced with Wannier 90. And you can divide these codes in two classes. On the one hand, you have what I call ab initio engines. You had things like Quantum Espresso, but also other codes like VN2K. It can be VASP. Most of these are DFT codes, but it doesn't necessarily have to be DFT actually. And they, they're your engine, your quantum engine. They provide you, the ground state charge density. They provide you the orbitals, the Consham Hamiltonian if you're doing DFT. And you interface this with Wannier 90 in a way that Wannier 90 is like totally, let's say, it doesn't care about the details of how certain quantities being produced. We will see which quantities, but you should already imagine what they are. If you think of the talk of Nicola yesterday, things like the overlap matrices, we will see the projection matrices. As long as you have a common format, it doesn't really matter the way you produce them. You plug them into Wannier 90, and Wannier 90 produces Wannier functions, especially maximally-localised Wannier functions, but not only, we will see that, and especially operators like the Hamiltonian or the position operator in a Wannier function basis. And once you have this, you can use it to calculate so many materials properties. Okay, so this is the school that is really about electron-phonon physics. So you see here listed FW that uses Wannier functions for interpolations, but it's really broad, the scope of quantities you can compute. It goes from DMFT, dynamic field theory, to GW calculations that here listed Yambo. There is a lot of software packages that are about topological properties and geometrical properties of the electronic structure, like baryology. There is Z2PAC here that some of you might know. There's Wannier tools. It's not even listed here. And so Wannier tools, and it's another one. You can couple this with AIDA for if you were interested in automation. There's really a long list, and as I said, this is not a complete list of codes that are interfaced with Wannier. And the message that I will try to convey this during my talk is that the way this is going on is that more and more properties are actually being implemented outside Wannier 90, so in software packages that are around. And this has always been a little bit like this, in the sense that by the very nature of Wannier functions, you know, the whole schema is really adapted to do something like this, where, you know, have a core packages and then other packages around. But I think we're bringing this to the next level. Okay, so I will not give you again an introduction of formal introductions to maximally-localised Wannier function, but this is just a very quick recap to sort of remind you of the lectures of Nicola yesterday. So we start from the electronic ground state that you get from first principle simulations, for instance, with quantum espresso. You do a subspace selection and unit transformation of block wave functions, okay? And this is the formula, okay? If there is one formula about Wannier functions that you want to remember, I think is this one, okay? So you have your Fourier transform and your unitary transformations, and then you get this maximally-localised Wannier function in real space, and they are maximally-localised as long as you choose these unitary matrices UM and K, such that they minimize the spread function, which is this object here, okay? So you start from block functions and you get to Wannier functions, okay? Now, in practice, there is some mathematics involved. This was, you know, Nicola told you yesterday about this. There are two parts in the spread function, a gauge invariant part and a gauge dependent part. And if you study, for instance, insulators, you just minimize this gauge dependent part. And if you do the mathematics, you discover that everything is just, you know, the most important quantity is the overlap matrices. The overlap matrices between the periodic part of two block states, okay? And in the iterative minimization, what you do is just update this overlap matrices, and you update this matrix with this, again, unitary matrix U, okay? So for instance, for insulators, in principle, this matrices could be sufficient to do the whole process. But in practice, you need projections. This this has been introduced by Nicola yesterday. You need especially an initial gauge in any case that is smooth, and this is something you can achieve with projection functions. But also in the case of disentanglement, you need an initial subspace. Okay, so in any case, in practice, this is never sufficient, and indeed you need to specify a projection, a set of localized projection function on which you project your manifold of states. Okay. And then this creates this new matrix. This is called the AM and K matrix. That is again quantity that you need as input in Wannier 90. Okay. In the past, it used to be mostly produced again with these projection functions like atomic orbitals, essentially SP, D, SP3, depending on the chemistry of your system. This again something Nicole discussed yesterday, but I will present today a more recent method that actually can deliver this overlap matrices without any, manual input. Okay, you just turn on this algorithm, and then it will provide these matrices for you. And then once you get this, you orthogonalize a little bit your rotated states, and you have your initial unitary, semi-unitary matrix here, and you start with your Wannierization as usual. So you minimize the spread function. So who's supposed to do this for you? Well, it's as I mentioned before, one option is to use Wannier 90, which is, as I said, I think the reference code to calculate the maximally-localised Wannier functions. And if you want to, to approach the code and approach this kind of calculation, I think really the place where you have to start is the Wannier website. Okay, trivial, you might say, but really this is really, a must if you want to go into Wannier function, because you find 90% of what you need to get started. Okay, so of course you find the code, okay, which is very light. It's a few tens of megabytes, I think. But especially you find the link now to the GitHub page of Wannier 90, okay, where you find the developed version. And I will comment on this Wannier 90 repository in a few slides. But also on the website, you find the user guide, which is, I think, really well done. For each variable of the code, you find a description, actually an explanation of what it means, and then a description of how you have to set it up, basically. So this is really very, very useful. If you do, if you work with Wannier functions, it's always there. You constantly look at it. Then there are many tutorials. I think we reached 30 or so, more or less, that these tutorials, they try to cover most of the functionalities, if not all the functionalities that are supported by the code. And for most of this exercise that you find in the tutorial document, there are also solutions. I think we have to thank Valerio Vitale for this, for putting together all the solutions. Okay, so for the most of the, for sure, for all the important functionalities, but also more niche applications, you find the solutions of the tutorials. This is, I think, it's very useful. So there is an email, a mailing list. Okay, so the community that I really recommend you to subscribe to if you're interested in mining functions. This is very low traffic. It's like orders of magnitude fewer emails than the Quantum Espresso mailing list, so it's safe. You can register without being overwhelmed. But really, I think this is very useful, again, to ask questions to people working in the field. And you know, in terms of publication, this is the most recent reference. Was we mentioned yesterday. This is, you know, the reference about the code, where also you find the descriptions of the most recent functionalities. Okay, so please, you know, cite if you want this paper if you use one of the recent versions of Wannier 90. Okay, so historically this was you know, was started by Nicola Mazzari, who gave the talk yesterday in 1997 with a maximally-localised Wannier function method. And you know, for many years it was really something developed by a core group of people. You know, there was Nicola, there was David Vanderbilt, there was Ivo Sousa. But then a few years later, some other people joined and they rewrote the software in modern Fortran and Fortran 90. And this was mostly driven, I think, by Arash Mostofi and Jonathan Yates. But over the years, some other people sort of joined in, especially Giovanni Pizzi, who really was a driving force of the Wannier 90 project, and even more recently, Valerio Vitale, who was a postdoc in London and now actually is coming to as a Marie Curie fellow at the University of Trieste. So there is a core group of developers, but over the years, you know, many more people sort of joined, and to the point that, you know, it was decided to move Wannier 90 from a regular open source code, electronic structural code, if you want, to a community code, where really the development is driven by the community, very large community of people who contribute to this. And you see, you know, indeed, if you look at the most recent publication, there's really a lot of people involved at this stage. Okay, and you know, a lot of these people they don't do Wannier functions 100% of the time. Okay. And an event that triggered this was the coding week we had in San Sebastian 2016, where it was essentially an event that helped a lot to put the code on GitHub and transition to a community-driven open source code. So what this means for you is that, first of all, you can be a contributor. You can be, if you want, a passive user, so just download the code, you know, run the code, do what you want with it. But if you want, you can contribute very easily these days. Okay, it can be just, you know, fixing bugs and reporting bugs, but also adding new features and you know, and improving the code, or adding new functionalities, or even sometimes asking, you know, I would like this to happen. Is there anyone who wants to sort of work with me on the topic? And you know, it's really, we support a lot this. So you should really, if you're interested, and I think many of you in the audience, not just the core developers of PW, could be interested in actually in adding new functionalities or, you know, working on this. So really we push for people to contribute to the code if they wish. In terms of, you know, going a bit more in practice, what are the features of Wannier 90? Of course, it's mostly about calculation of maximally-localised Wannier functions. So you find this, the algorithm of Nicola Mazzari, David Vanderbilt for maximally-localised Wannier functions, but also the extension to metals and conduction states, and that was put forward by Ivo Sousa with Nicola and David. So this is the famous disentanglement technique. And then, you know, we go on with more and more technical sort of features. You know, there is optimized version of the algorithms for gamma point calculations. Of course, you can actually do, and this might be of interest for you, for some of you, only projection only Wannier functions. So you're not forced to do maximally-localized. There are many choices these days. Okay, and in some cases you don't necessarily want to do maximally-localized. This is very important. You can print, okay, the operators like the Hamiltonian or the position operator in a real space Wannier function basis. This is very useful for a number of applications, especially tight bounding calculation, but not only. Spin or Wannier functions are supported, so you can do calculation with spin coupling, of course. There are some utilities to export this Wannier function, look at them, you know, by plotting them, and then we go on with more sort of advanced application. What I want to sort of emphasize are some of the new features that are these ones that I highlighted. First one is symmetry-adapted Wannier functions. I will briefly overview some of this. And again, this has to do with the fact that these maximally-localized Wannier functions are not the only choice you have. In some cases, you might want to prefer to have a little bit more symmetries in your Wannier functions and less localized Wannier functions. Okay, so the spread is a little bit higher, but the symmetries are there. And then something I will discuss more in detail is this SCDM method that is a way to get Wannier functions without the need to define initial projections. Okay, this is a new feature that is implemented already in the code and is publicly available, so you can use it since at least a couple of years, I think. Well, maybe a year and a half. And then just mention that, you know, Wannier 90 used to be a serial code, but now since has been ported to MPI, so you can run Wannier 90 in parallel, and this gives quite some speed up, and especially because the core subroutines of the Wannierization have been ported by MPI. And something that could be more relevant for you interested in electron-Phonon physics, there is a lot of tools for interpolation, essentially. So density of states, like band structures. You can project the density states and the band structures on your Wannier functions. Okay. You can interpolate the Fermi surfaces, and these are the features that we will explore with a hands-on tutorial later on this morning. Okay. So band structure interpolation and Fermi surface interpolation. But I want to mention that more recently we also support GW bands interpolation. So what is supported from the point of view of Wannier 90 is an interface with the Yambo code, which is a many-body perturbation theory code, very similar to, if you want, to Berkeley GW. Okay, so this is, if you want, what is supported in the sense that, you know, I personally actually work on this, prepare a tutorial, you know, where you do interpolation of GW band structure silicon. But I was discussing yesterday with some people from Berkeley GW, I know where they are, that actually there is something very similar in the Berkeley GW sort of code or on their community, and probably at some point we'll actually merge everything and have a you know, a unique interface. I don't know, but let's say this is these days more and more relevant. I think people are shifting from just calculating DFT band structure to more advanced methods, and just wanted to emphasize that, you know, you can interpolate, of course, GW band structures with Wannier 90. There are properties that are more of interest for people doing baryologies, you know, and topological materials. You know, listed here, Berry curvature and anomalous conductivity, orbitamization, and much more. There's a lot of subroutines related to transport. You know, ballistic transport, Boltzmann transport. The Boltzmann part was a contribution of Giovanni Pizzi, and more recently also the spin-off conductivity. Okay. So now, after this quick overview of the functionalities of the code, I would like to update you on some recent developments that are particular. Trying to choose the developments that are more relevant for people like you here who are interested in interpolations. Okay, so with Wannier functions, you can do many different things, and Nicola gave an overview yesterday. But one of the most common applications is interpolation, and this is what I think is more of interest for electron-Phonon physics. So, you know, Wannier interpolation is kind of Fourier interpolation, was introduced yesterday, is kind of discrete Fourier transform. And if you know the basics of Fourier transforms, you know that you can reconstruct faithfully a continuous signal from a discrete sampling, provided that the signal has a finite bandwidth and that the sampling rate is at least twice the bandwidth. And this is the famous Nykish Shannon condition. Okay, so you have a signal. You know, let's imagine a periodic, not really a periodic, more like an audio signal. Okay, if you go to frequency space and there is a maximum frequency, just take twice that, and with the inverse of that gives you the sampling rate that you need to have. And what is important here is that if you sample with that sampling rate, you can reconstruct perfectly a signal. There is no loss. And the same is true for Wannier functions. So you have a quantities in reciprocal space. For sake of concreteness, let's take the Hamiltonian. So you have your Hamiltonian on a set of k points. You can Fourier transform it in real space, okay? And this is equivalent to just taking the expectation value over Wannier functions, okay? And as long as your grid in reciprocal space is dense enough, so it's a coarse grid in general, but it needs to be dense enough. Once you go to real space, okay, you will work with a Bonfort-Karman supercell, and you will have matrix elements of your Hamiltonian between a Wannier function M and a Wannier function N sitting at the direct lattice vector R, as long as you in this bomb for gamma cell, you include all the relevant hopping. So whatever is outside is vanishing small. Once you do the inverse Fourier transform, you go back in reciprocal space. You can get the Hamiltonian at any k point at no cost, essentially. Okay, so you can do the inverse Fourier transform at a given k point. You just diagonalize this Hamiltonian that you get, and that's your band structures. Okay, interpolated band structure. And this works because when your function are exponentially localized, so there's an exponential decay with the distance in real space. Okay, so you need a really finite coarse grid to do this. So this has been introduced already yesterday. What I want to tell you today is that there is a tiny detail that is not specified if you look at this formula that is actually very relevant for the quality of your interpolation, and this has to do with which Wannier functions you have to consider. And so if you look at the formula, it just says you need to Fourier transform your real space Wannier function, but it doesn't tell you on which direct space direct lattice vectors. In principle, they are infinite. In practice, you just take a finite set of vectors until the matrix elements are 0. But even more in practice, what was implemented in the code, at least in the public version of the code, was that you take your cell, the primitive cell, you do a finite sampling with a uniform finite sampling in the Brillouin zone, and this corresponds to a Bonfort gamma supercell. And these R vectors were just taken to be vectors of the inside this Bonfort gamma supercell. And this is an example. This is a 2x2 Bonfort gamma supercell corresponding to a 2x2 grid. And if you now think about, you need to consider the hoppings between Wannier function N and a Wannier function M. If you think for a second, the nearest neighbor Wannier function N might not sit in the Bonfort gamma supercell, but might sit in a neighboring Bonfort gamma supercell. Okay, and this was not considered actually, and so this formula has relatively recently been modified to this formula here, which seems a little bit complex, but essentially it's equivalent to just say that we consider now the Wigner-side supercell of a given Wannier function. So for a given Wannier function M, you just look at the nearest neighbor in also neighboring Bonfort gamma supercells, and this is what this T vectors does. You try to find these T vectors that minimize the distance between the centers of two Wannier functions plus direct lattice vectors plus a vector T, okay, where this T brings you from neighboring Bonfort gamma supercell, okay. And so in practice, this has an impact, okay. It might seem something a little cumbersome to understand, but if you think at the limit of gamma sampling, that corresponds to just have sample at gamma, you see that this formula here would give you flat band structures, okay, which is of course wrong, while this formula here converges to this limit here, which is correct, and it gives you this orange band structure here that reproduces the of course the first principle DFT direct calculations, okay. So it's clear in the gamma only limit, but as consequence also for your everyday use with periodic solids. For instance, this is an example of silicon under converged, so it's a 3x3x3 cell, sorry, 3x3x3 k-point sampling, and you see that the blue line which is the interpolation with the old naive method, is very far from the true DFT band structure, which are the crosses, okay, here. While the orange one is the current implementation, and this is much closer. This is still under converged, and indeed, in the limit of very, very fine meshes, the two approaches are equivalent. But given that all this business of Wannier interpolation is about using coarse grids, I think this is particularly relevant. So it gives you with a coarser grid much more accuracy, or if you want to say it the other way, given a grid, it improves accuracy. Indeed, that you get better interpolation, but especially better degeneracy. Okay, and this is, as I said, especially true for very coarse grids. Since recently, this is the default approach in Wannier 90. So this is what you do. Even if you don't, if you don't ask Wannier 90 explicitly, this is what it does for you. One of the reasons why I want to mention this is because you see there are other quantities that now are relevant to do the interpolated band structure. There is this degeneracy number here. There is a set of T vectors, and this is additional data. And if you want to use the Wannier Hamiltonian to do interpolation or other things outside the code, there are other files that are now printed, or there is a new format to print the Hamiltonian that includes this information here. Okay, so this is something that is has changed over the last few years. So now I want to talk a little bit about symmetry-adapted Wannier functions. This is again, well, I would like to say it's a recent approach, but it's not recent anymore in the sense that some of the early efforts are from 2013. So it's actually something that has been going on for quite a while. So, as I said at the beginning, maximally-localized Wannier functions are one option. You can decide to maximalize your Wannier functions and to minimize the spread function, but this is not by far the only option. You have many other options. And one of this is to enforce symmetries. And one of these approaches is actually called symmetry-adapted Wannier functions. This was proposed by Sakuma, as I said, in 2013, so not really a recent development. And it's really, the mathematics is a little bit too long, probably, to be discussed today. What we'll just say is that it's essentially, it puts additional constraints on the unitary matrices UK during the spread minimization. Okay, so these are your unitary matrices. Now you don't just take them, but you manipulate them with objects that are the matrix representation of your symmetry operation G, and another object which is represents how the block states are transformed by the symmetry operation G. Okay, so it's a more complex approach. You need to print additional files, especially in PW290. We will see during the tutorial what PW290 is, but essentially, for the moment, just think of it as a code that enables you to interface quantum espresso with Wannier 90. So you need to print additional files. It's a bit more complex, but it's available, and in a number of cases, it's actually something you might want to explore. There is a more sort of naive approach to go towards symmetric Wannier functions, which is called the selectively localized Wannier function. This is in principle not really related to symmetry, because it's just a very minor modification of the maximally-localized approach, where you just decide to selectively localize a subset of Wannier functions. So you have your spread functional, and you just maximalize some of these Wannier functions. And this was discussed in this work here by Bang in 2014. Now, but if you couple this, especially with constraint centers, so now you add the penalty term on the deviation from the predefined center. So it costs you some some energy if you want to move to have centers that are not where you want them to be. If you do this, actually, it turns out that these Wannier functions are very, very symmetric. Okay, so this helps a lot to have more symmetric Wannier functions. And I will not go into the mathematics of all of this. I will just show you one example, which is the gallium arsenide, and where people try all the different approaches and they compare the results. So here you see this is the results for the maximally localized, this for the symmetry adapted, this is for the selectively localized, and this for the selectively localized plus constraint. And of course, the most important column is this one, is the total spread. And it's so it's reassuring to see that the maximally localized, of course, yield the lowest spread. You see this one. But if you look at the other approaches, this spread is not orders of magnitude higher. It's something like 10 with respect to 7 angstrom square. Here it's almost 10. And in this selectively localized plus constraint centers is 7.9. Okay, not so much more delocalized than the maximally localized, you see. And actually, individually, you can have Wannier functions that are more localized than the maximally localized. So the maximally localization enforces that the total spread is the lowest possible you can find, but individually, the Wannier functions might not be the most localized. And indeed, with these other approaches, you can find lower spreads in some cases. Okay, and while here you see, of course, to compensate, the other kind of Wannier functions have larger spread. And then if you look at the centers, you see of course, the maximally localized are not atom-centered, but the others are. So the symmetry adapted are centered on the atoms, and in the symmetry, the selectively localized with constraint center might be in some cases. Okay, depending on how much you enforce this penalty term. And this is so wanted to show you this example because, of course, the more localized your Wannier functions are, the coarser the grid you can use, the more efficient is the interpolation. But if you're interested in something like degeneracy, or you have models where there are many cases where you would like to have, for instance, atom-centered Wannier functions. In those cases, you might sort of be willing to pay the price of having would say, less coarse grid, a little bit more tensor grid, so a more expensive for spin calculation, but at the same time to have the symmetries right and to have a lot of degeneracy sort of enforced. So this is again something I think it might be interesting in the future. Now I will move to a different topic. This is has to do with this SCDM algorithm that I mentioned, and I will we'll start with this title is called Hunting for Projections, because indeed all the Wannierization machinery works very well, but if there is one bottleneck, is indeed the choice of initial projection. And the reason why this is the bottleneck is because it needs, in most cases, a lot of chemical understanding and a lot of experience in some cases. And this is the biggest challenge for new users. Okay, so if you approach the code, this is really what the thing you have to learn. The rest is more or less straightforward, I would say. And this has been very hard to automate. It's been very hard in 25 years to find recipes to automate this. And if you look at the the mailing list, most of the questions by the users are on this. They ask for help on how can I define the correct projection for this particular material? What is the correct projection for graphene? What is for this other material? So what I will discuss now is a recent method. It's called SCDM, which stands for Selected Columns of the Density Matrix. That aims. This was proposed by Emil Damle and Lin, and aims at giving, let's say, an algorithm to automatically find Wannier functions. Okay. And Lin, I mean, is a mathematician, so it derived this from pure mathematical arguments, from linear algebra, from these considerations. So I will not, use his way of explaining things because I didn't understand it. So actually, what we did when we implemented this in Wannier, and as I said, this is now implemented and available, we tried to sort of re-understand what he understood first in a more physicist sort of from more from a physics point of view. So I don't know if we will manage to convey why this should work, but I will do my best. So let's start from something simple. We consider insulators, and the density, the one body reduced density matrix of insulators. So just the projector over your occupied states. It's a projection, so it's idempotent. So very simple object. Now you just represent it in a real space. You just have your real space grid, and you take this projector and you look at the columns of this projector. And this is where the CDM part of the acronym is column of the density matrix. And if you take a column, is equivalent to do the product of this density matrix with a delta function localized on a specific points in your real space grid. Okay. Now, what is interesting is that this column is localized. It's a function that is localized in real space, and all of these columns are localized. It's just that they're not orthogonal to each other, absolutely not, but they are localized. And if one wants to find like a reason why this should be true, I mean, of course, this has to do with this concept of near-sightedness of the density matrix, so that especially for insulators, all density matrix goes decays in real space in an exponential way. That is here put some references, but practice. What is interesting for you is that the columns of a density matrix of an insulator decay. They are very localized, and the density matrix decays exponentially. So they are localized function. We might think that this could be good projections. But let's look at them. And unfortunately, this is not. Yes, there was a video here, but this is a PDF, so it is not shown. Okay, cannot show it to you. But essentially, if you took a simple example like silane, and you look at the isosurfaces of these columns of the density matrix, unfortunately, it's not seen in this slide. You will see it later. If you look at the isosurfaces, they really look a lot like the Wannier functions, actually the maximally-localised Wannier function that you would get with the standard approach of specifying projections. Okay, so it seems interesting, that these columns might be something relevant. And we said that they are localized, so one could think, okay, we take n of them, and we are good. But the problem is that you need to take n linearly independent columns of the density matrix to get a localized basis, and that would be enough because that would span the space of your projection. So how do you do this? You cannot choose these columns randomly. We said that they are very overlapping. They are in some cases almost linearly dependent. They are definitely not orthogonal. So the point of the SCDM is to try to find the most representative columns, okay, the one with less overlap between each other. And this is what this is the idea of Lin, to use this QRCP algorithm. So it's a QR decompositions with column pivoting. You have your projector P, and you decompose it in a Q matrices that is orthogonal in an R matrix that is upper triangular. And then there is this column pivoting that adds this permutation matrix that swaps the columns such a way that these diagonal elements of the R operator are decreasing in magnitude. So you have the first diagonal element is the largest, and then the second one is smaller, and then the smaller, and so on and so forth. And then you take the first n columns of this, and these are the most representative columns. Okay, they are the most orthogonal columns you can find in the density matrix. Of course, they are the most orthogonal. They're not exactly orthogonal, so you do, in any case, a load in orthogonalization to make things really orthogonal. But it's it's a fine tune. Let's say it's a refinement, but they are almost very orthogonal to each other. And this is for gamma only, but you can easily extend this to the case of k points. Here you see, by the way, this were the selected columns of the density matrix for Silane. You see, they really look like the maximally-localized Wannier functions. Okay, this was good for insulators, and we tested this. So of course, we didn't want it to run each material by hand, so we automated the protocol with AIDA, to just speed up things. And we did more the anti insulators, the band structure of the valence states. It works very well. We tried different materials with different symmetries. We tried to explore a little bit the material space. It works. But if you work with functions, you know that insulators are the easy thing. Where other approaches more or less would have helped. It's good to have a new approach, but this is not what really was people were looking for. The important part is to solve the entangled bands case. So metals and conduction states for insulators. So, and what is interesting about SCDM is that for metals, it more or less works the same way. There is just one tiny, if you want, formal change, that now your density matrix is modified, and you apply a window function. Okay, it's a bit like applying smearing to the density matrix. Okay, so you put a window function that is a smooth function of energy, and that selects the states you're interested in. And if this window function is smooth, then of course the density matrix decays rapidly. Okay, it's a bit like using smearing. It's like if you have a metal, you think about smearing normally in a different way. You put smearing, so it's easier to sample. A function that goes from occupation 1 to occupation 0. You just have a smooth occupation function. But in a real space picture, one way that personally, this is the way I think about smearing in real space, is that you have the density matrix of a metal that doesn't really decay so rapidly. You add a window function, or you add smearing, and this causes the density matrix to artificially kind of decay much faster. Okay, but it's just a formal thing. You add some window function, and then you keep so you go back to the SCDM, and it's the same algorithm. There's no change. You go on with the same algorithm, and you choose your columns of the density matrix. This window function can be anything you want, as long as it's smooth. It can be a Gaussian, for instance, if you want to select some specific states. In most cases, what we do is you use an error function, which is this one here. And the error function, of course, has two parameters. Has the center of the transition here. You see, goes from 1 to 0, and this is the center. And then it has the width of this transition here. Okay, so these are two parameters. And then, of course, for metals, you need to decide how many Wannier functions you want to Wannierize. And the SCDM algorithm was shown to work very well. But of course, what was left to figure out was how do you select this parameters. Okay, so the number of Wannier functions, the mu parameter, and the sigma parameter. Okay, and so what we studied a bit the problem. We noticed that the SCDM is a good algorithm in the sense that it doesn't depend on the on the fine tuning of this mu sigma. There is some freedom. There is a region of stability, but you cannot set them randomly. Okay, if you do, you don't get good interpolation. If it's too small, the mu, you don't consider enough states. If it's too large, you get these high energy states that pull up the band structure. So you need to find a way to actually tune this, and you like to do this, of course, automatically. And so again, we come back to to the basic ideas of projectabilities. They're always there with a function. So we take the quantum states and we project them on the atomic orbitals that we have in the pseudo potential. Okay, so we project them with a pseudo atomic orbital. Well, we do something very brute force. So we just sum all the projectabilities of all the atomic orbitals that we have in the pseudopotentials. And this gives you a function that is 1 if you consider the low energy part of the spectrum, then it will be 1, 1, 1, 1, 1, and then at some point it will jump to 0. You see it here. And it will jump to 0 when you start to have states that do not really project on your pseudoatomic orbitals, okay? And this quantity here, these projectabilities, are easy to obtain with quantum espresso through this projectability x.x executable. It's something easy to obtain, and we fit them, okay? So, but before I go to the fitting, we need to make a choice for the number of any functions. So we choose the number of functions to be equal to the number of atomic orbitals for which we have information in the pseudopotential file. This was not really a new idea. You see some references here, but you need to choose something. And then we compute this projectability that I've shown you for each state of the projection of, we compute the projectability of each state as the projection of each state on the subset of the atomic orbitals that you have in the pseudopotential. Okay, you get this function here, and looks, it looks a lot actually like an arrow function, and you can fit this with an arrow function. You get the width sigma and you get the mu. And what we do is that we take a mu that is not what you get from the fitting, but is 3 sigma lower. And this way make sure that our window function includes as many states as possible that project on the pseudoatomic orbitals, but we make sure that there are no states included that do not project on atomic orbitals. If you want, this is the recipe in a sense. And yeah, so we select, okay, these parameters. And then we validate this with a simple example. This is tungsten. This is the spread as a function of this mu and sigma. You see that there are regions of stability, in a sense, regions where, you change a little bit, the parameters and the result doesn't change much, which is good because it means that the approach is robust. But you cannot set them randomly, you see. You can have regions like here where the spread is very low, and you might think this is a good thing, but this is not, because this corresponds to a very inaccurate band structure. This band distance, I will define it in a few seconds, but essentially it's a measure of how good your band interpolation is, how your interpolated bands are similar to the true DFT bands that you obtain from direct calculations. And so with our approach, with this protocol, we are here, okay? So we are in a region where spread is more or less flat, but the band distance, so the quality of interpolation is very good. It's in the region of the parameter space where the interpolation is most accurate. And again, we automated this, and with it, we explore more than 200 systems, both metals and insulators with conduction states, trying different symmetries, structures with crystalline structures with different symmetries, different number atoms per superset, trying to explore a little bit, to see if there were cases where this will not work, and it works pretty well. I will not show you all the statistics. I will just, summarize that, with our metric here is the band interpolation. So we define this band distance as the quadratic. It's kind of a mean square error between your DFT bands and your Wannier bands, and we check if on average this is very low, but also if with the maximum distance, if there are any specific regions of the K-space or any specific energy windows where this error maybe is very high. What was also you need to automate is the choice in the density of K points. You need to decide, in general, how dense must be your grid. And this is also this screening was also a way to understand this. So you find some results for the maximum distance and the average distance as a function of, well, this is a histogram, but you see all these plots are with different sampling in the reciprocal space. Okay, different density of K points. I will not show the results for insulators. I will just tell you that we tested that. It's actually, in that case, SCDM is already very good. You don't need actually to maximally localize Wannier functions for insulators. If you use SCDM, they are more or less already very well localized. But this is for metals and in general entangled bands where things are a little bit more difficult. And you see that the errors are very low. In general, the approach works very well. You can do maximally localized on top. So the blue ones are just SCDM, just projected on projection only Wannier functions if you want, and with the red one are with the full minimization of the gauge invariant part of the spread. So maximally help, but in general they are very good. And with this 0.2 x minus 1 sampling, you already get very good interpolation quality. So this is available in Wannier 90. You can use it. The optional exercise of today, exercise 4, is about this, in case you're interested. And it is a way to automatically get the projection for the projection matrices AM and K if you don't know, if you don't want to think about the chemistry of the system. If you don't know where to start from, this is something that does the work for you. And again, as I said, you don't have to do it by hand these days. This is all automated with AIDA. You will not discuss this today, but you find it. You find all the workflows, all the tutorials, this page, and you find very detailed exercise that can guide you through the protocol. But to summarize it, these days you can take a crystal structure, give it to a workflow, and it will give you maximalized Wannier functions for you. And you don't need to care too much about what happens in the middle if you're interested just in advanced structure interpolation. If you want to do, of course, more advanced stuff, you still have to, to do it by hand or say to interact at some point during the workflow. Okay, so this was more or less what I want to say about things that are there, that have been implemented and are available. Now I want to give you a very quick overview of what is happening right now and where I think we are going to. In terms of what is happening right now, what has just happened, we had a Wannier summer school in Trieste just a few weeks ago. This was the 3rd week of May. And as you see, it was a Wannier summer school. It was not a Wannier 90 summer school. And really, what the idea that we had, when we designed this event, was that we want to have an event that was beyond Wannier 90. Was trying to sort of attract this entire ecosystem of packages that are that have been developed around Wannier 90. So we had 50 students present. We have 50 students connected online. A lot of speakers. You see here the list. You see the topics. We covered, of course, maximally-localized, but also advanced Wannier function techniques, the symmetry-adapted, the SCDM that I just sort of shown to you, transport. But also we had things like tight binding models, topological properties, Berry phase, Electron-Phonon coupling. Of course, Roxana was among the directors of the school, and there were tutorials on OPPW, but also dynamic field theory. We had all these different things, very different, heterogeneous set of topics, if you want. What they all have in common is that they really rely a lot on Wannier functions, and in some cases, maximally-localized Wannier functions to operate. Okay, and if you want to explore, you're interested in Wannier functions and you want to study the subject further, I recommend you to go to the website here, the ICTP website of the school, or to the YouTube channel. You find all the lectures recorded and available, and in some cases also the slides in PDF. So really, now the effort is to put together a community of people. It has always been like this, but I will show you now why this has become really timely. Why we really have to do this right now on a different scale. After the school, there was a developers meeting again. We had people not just working on from Wannier 90. We had people from IBM working on quantum computing, people doing Berry phases, embryology, people doing Electron-Phonon with different codes. We had really different people studying magnetic system and doing effective Hamiltonians to include magnetic interactions. And again, if you're more an expert now and you want to get to get updated on the recent developments, some are very interesting, and I couldn't talk about it today, like the Wannier function perturbation theory, for instance. You can go on this other website and you find all the talks that were recorded during the developers meeting. Okay, and this you see is where some of the working groups we had, where we try to tackle some of the challenges that are not just in Wannier function theory or Wannier 90, but again in more general challenges related to Wannier functions. And again, as I said, when I started my presentation, of course, the way Wannier functions are produced is, leads you to this idea that you take any ab initio codes that you want, you compute your overlap matrices, you compute your projection matrices, you compute your eigenvalues, and then you go on with the Wannierization. Okay, so it's very natural to decouple things in different software packages. But now it's what is happening, thanks to this probably, and thanks I think also to the fact that we had this open source Wannier 90 code was very robust and available. We're spontaneously going towards a more decentralized software ecosystem, as opposed to a model where you have a monolithic Wannier 90 code that does everything. We didn't, I think nobody planned it this way, but this is what is happening. And this has some consequences for all of you, both users and developers. One drawback is that there is always some small duplication of efforts, multiple people doing the same thing in different codes. That always happens. But it also means that if you want to compute something that is related to Wannier functions, it might be likely have already been implemented, but maybe you don't find it in Wannier 90. So these days you actually have to check existing packages of this either or this broad Wannier ecosystem. You find a partial list on the website, but we're trying to sort of screen a bit what is out there. You might actually want to check other packages that do things that are related to Wannier, but they're not in Wannier 90. And not all the implementations are equals. Okay, there are newer implementations that can be orders of magnitude faster. I'll give you one example, that is related to tight binding motors. There are 2 Python codes to do tight binding, or that tight binding ab initio, in the sense essentially reading the Hamiltonian from Wannier 90 and diagonalizing Hamiltonian and doing ab initio tight binding. One is TB models, one is Python tight binding. And TB models was developed just because Python tight binding was not fast enough. Okay, and of course they do not have exactly overlapping functionalities. But if you want to study large systems, you need to use one package. If you want to do other things, you need to use the other package. And the same is true for this Wannier Berry that does a lot of this Berryology, Berry curvatures calculation, anomalous conductivity, and many other things. And a lot of this was already implemented in post-W90, which is the post-processing code of Wannier 90. But the author of this, which is Stepan Sirkin, at some point, he was frustrated because post-W90 was not fast enough, and he decided to rewrite everything from scratch and have a code that is orders of magnitude faster again. So, this is a consequence. Sometimes things are outside Wannier, but you need to check before re-implementing the wheel again and again. Then, I think in general this is good. So I use this term biodiversity. Okay, biodiversity and software is good. I think the copyright of this goes to Gonze, if I'm not wrong. So this idea that having different code doing different things is good. And in this sense, even though sometimes there is duplication of efforts, it's good sometimes to have different packages doing things when a function that sort of check each other. That they make sure that think they're doing the right thing. And sometimes you might find packages that stop being maintained. The typical case is that the authors of the package goes to industry, and this has happened. But in general, the fact that there is some duplication of effort, that there is, all these existing packages are sort of independent from each other, it makes sure that the whole Wannier ecosystem always survives. So you can always operate, calculate things. It's very robust overall. And this is a bit, a message to, how all these Wannier packages are running. Okay, future directions, something that is will soon be available in Wannier 90. Symmetries. This is not the symmetry-adapted Wannier function that I mentioned already. This is more basic. It's just that, as in most electronic structure codes, you would like to just work with the irreducible Brillouin zone. Okay, and for a number of reasons, this was not there in Wannier 90. So historically, Wannier functions required you to work with a uniform grid in the Brillouin zone. This is what you will see in the tutorial later on today. But now there is an implementation by Takashi Koretsune, which is complete. Actually, it's a complete implementation. It will be merged probably in the next few months, where you simply calculate the projection and overlap matrices on the reducible wedge in the Brillouin zone, and then you unfold it. Okay, and this has a consequence for the users because the most expensive part of calculation is the DFT part. I mean, Wannierization is very fast, and in some cases also this interface PW to Wannier 90 might be quite, I would say a bottleneck, but it can take some time to compute these matrices, and this helps a lot to speed up that part of the protocol. Okay, band parization. There were already, as I said, sometimes having an ecosystem means that people do things twice. So there were 2 existing implementations of band parization PW to Wannier 90. This is now being merged into a single one, and again for the users, this means that you will be allowed probably, you will be enable to run PW to Wannier much faster with this parization. Something that is worth to mention, not really for users, but more for developers here, of PW, for instance, is that the code is now being restructured extensively, in the sense that It used to be a code mostly run as a standalone code. So you have your input, you have Wannier 90, you have your output. And there was also a library mode that I think APW uses, where you can load, you can call Wannier 90 as a library and then do your own thing. Now this will change drastically. This is work done by Jerome Jackson and people at SFTC in the UK and Arash Mustafi and other people. It's the new Wannier 90 will be essentially a library. And the problem was that a lot of functionalities were not supported in the library mode, but now everything will be library, and the standalone code will just be a wrapper of the library. Okay, so this I think will have an impact of people using Wannier 90 as a library. And then there are many other now functionalities will be merged, but just the last one I want to mention, there will be probably a unified Python interface for Wannier 90. There were many, that will be just a unique one supported, a very well supported Python interface. Okay, so last slide. This is just my personal take, sort of personal opinion. It's not does not reflect the opinion of the Wannier community. It's just my thoughts. I think in the future we will trade some localization. This is, I think, a message I tried to convey already during the talk. We'll trade localization for symmetry. Will be more and more interested in less localized Wannier function, but more symmetric and especially atom-centered Wannier functions. So really, I think a lot of people are interested in having Wannier functions that are centered on the atom, especially for interpolation applications. Initial projections will not be a problem anymore. For 25 years, this was the major problem with Wannier functions. Now there is SCDM. This is already available in the code. You can use it already with the current version of the code, and this solves most of the problems, I think, for most users that are only interested in interpolating the band structures. But in the future, there is this work Nicola showed yesterday about this projectability and when this will probably be even more accurate than SCDM. But this is not there yet. So I think if you want to do something automated today, you need to use SCDM. And finally, given that the code is being restructured as a library, we will use it more and more as a library. But again, also from the point of view that there is now this growing ecosystem of more and more software packages dedicated to calculate specific properties, I think that probably many functionalities will be implemented outside Wannier, and Wannier 90 will probably become like again an engine to get Wannier functions, a little bit like APW operates, but this will be more and more true for the rest of the community, that used to use Wannier 90 really as a standalone code. Okay, so in a sense, we're going back to the origin. This is a quote from TSL that I really liked, and I think describes more or less what I want to say here. We in a sense, with the whole Wannier function business started, before Maximally-localised, and we are sort of going back there. Now probably we're not interested too much in maximalization, but more in symmetries and stuff. And we go back to just Wannier functions. Projections, we go back again to this idea that you just need very good projectabilities and ways to use these projectabilities in a clever way. And again, using Wannier 90 as a library in the sense that I think when Nicola said that yesterday, he was interested in linear scaling methods when he started this. And I think now a lot of the developments will of course, there will be developments, related to the theory of Wannier functions, but I think now most of the developments are on what you can do with these Wannier functions in terms of, clever things that you can do, also in terms of new theories based on Wannier functions. And so I think we're going back to that, just using them as a tool to do other things, because the biggest problem have been solved, projectabilities, initial projections, automation, it's all there, I think. Okay, thanks. This is what I wanted to say, and of course I'm open for questions.
Thank you very much for the talk. Any questions?
Thank you. Great talk. So I have a couple questions. Taking one at a time. When you describe the automated SCDM work, you talked about using the projected wave function.x method on espresso. gives you projections onto the atomic orbitals, but there may be materials where that might not be, these Wannier functions you want to get out of the method. So how does SC here, the automated SCDM method?
Well, I mean, if you want, there is this idea that behind that, we don't want to Wannierize like free electron states. We're interested in Wannierize relatively low energy states, and in general, things that project or map to localized orbitals. Because in the end, it's a unit transformation. So you start from something, and in the end, you want to get a localized representation. But if this object intrinsically doesn't have a localized representation because it's a plane wave.
So something localized, but maybe not.
No, but this is the point, and this is a very good question. You would take the sum over all the pseudo-atomic orbitals. So if it's sp3, we don't care because we are summing over s, we are summing over p. We are even summing over d orbitals if you have them in potential. So we don't care exactly which projection. We sum over all the pseudo-atomic orbitals. We just need to make sure that they project to some of the atomic orbitals that we have in the pseudo-potential. Okay. And this is why this can be automated, because we don't need to know the chemistry. We don't need to know if the Wannier function will be atom-centered, if it's going to be like silicon, like gallium arsenide. We don't really care. We just need to make sure that we are including states that somehow project on localized orbitals, because that's what we want. And we want to do it in a way that it's automated in the sense that we don't have to do it by hand. So I don't know if that answers your question.
Yeah, it answers.
Okay.
See every question.
Other questions?
Thank you very much for the talk. I have also a question about SCDM. Actually, I'm benefited from that. Thank you very much for this. Something that is very useful. For me, like I have a confusion about this part. Is like in my terms, like SCDM, you bring some random. Like when you do that for different times, like every single time has a different like result coming out. I don't know whether this is the correct one, and also my question is about like if this is how it would be, is that one from the algorithm or from the numerical?
So I'm not sure exactly what you mean by randomness. The sense that it's a deterministic thing. So in a sense, I think if you run it twice, you should get to the same answer. It might not be a good, let's say, randomization, but at least it should be the same. If you run the exactly same code, there is no like randomness intrinsic in this. What I think you might refer to is that indeed this is a brute force linear algebra thing. Okay, there is no so in a sense, which it just gives you Wannier functions. It doesn't give you very symmetric Wannier functions, for instance. So I give you an example. If you study, and I think this is discussed in the paper, like d orbitals, and you want to get the orbitals like Wannier functions. Some of the solutions for some materials might be, this is what SCDM will give you, 5 dz square orbitals, a little bit sort of distorted, such that they are orthogonal to each other, but they will not give you the dx y, they will not give you the nice 5. It will give you something that looks like this, dz squared, and 5 of those orbitals distorted such that they're orthogonal. In this sense, I think it's the randomness, in the sense that you didn't ask for that solution. It's just that some way the QRCP, the composition, gives you that solution. And maybe if you tune a little bit the parameters differently, it might give you maybe a different solution in terms of the way this sort of orbits look like. And this is why we think that the SCDM is very good if you're just interested in band structure interpolation, or in general interpolation. If you want to get interpolate things in K-space, the eigenvalues or other things. If you want symmetries, SCDM doesn't solve that. So SCDM will not give you very symmetrical functions. Sometimes it might do it, but by chance. But the way the algorithm is constructed is such that it doesn't give you symmetrical functions. So if you want, this includes a little bit of randomness. But this is especially for the entangled bands. I think for the insulating case, the solutions are sort of very similar to the maximally-localized. So I don't think there is too much randomness there. We can discuss later also for the details. Yeah.
think we have to move on first. So it will be great, but we still be time after. More so we can thank it.
Okay.